All right, today we're talking about something really cool. A brand new type of computer chip, one that was built from the ground up for the insane demands of modern AI. It's called the LPU, from a company named Groq. And honestly, it might just flip the script on how fast AI can actually be.
But let's start with something we've all felt. You know that moment. You type a question into an AI chatbot, you hit send, and you wait. You just sit there, watching that little cursor blink, knowing that somewhere a massive computer is thinking. With all the hype around AI, why does it still feel so slow sometimes?
Well, here's the thing. The problem isn't really the AI model itself. Nope. The real roadblock, the actual bottleneck, is the physical hardware it's running on. It's kind of like having a souped-up Formula One engine that's stuck in rush hour traffic. The power is there, but the road is just too clogged for it to open up and fly.
Okay, so let's dig into that traffic jam. For what feels like forever, the go-to hardware for all things AI has been the GPU, the graphics processing unit. But as we're about to find out, it might actually be the wrong tool for this particular job.
Now, don't get me wrong, GPUs are absolute beasts, but you gotta remember what they were originally built for. Video games. They're designed to handle millions of tiny, separate jobs all at once to paint the pixels on your screen. But running a large language model, that's a totally different ballgame. It's a series of massive, sequential math problems. Using a GPU for that is like asking that Formula One car to help you move apartments. Yeah, it's powerful, but it's just not what it was made for.
See, because GPUs are trying to be a jack of all trades, they're packed with extra stuff. Caches, buffers, all these things trying to guess what the AI will need next. All that complexity means their performance can be pretty unpredictable. And this creates a huge headache for developers. They have to write these super complex pieces of software called kernels for every single new AI model, just to manage all that chaos. It works, but it's a clunky, inefficient system.
So, what if you could just start over? What if you designed a chip with one and only one purpose, to run language models as fast as humanly possible? Well, that's exactly what the company Groq did. So let's meet the hero of our story, the LPU.
An LPU, or language processing unit, isn't just a modified GPU. It's a whole new class of processor. It's been engineered from the silicon up for the very specific way AI models think, with an obsessive focus on two things: raw speed and pure efficiency. It's not trying to do everything. It's designed to do one thing perfectly.
So how does it pull off this incredible performance? Well, it all boils down to four big ideas. Four core principles that totally rethink how a computer chip should work. Let's break down the secret sauce, shall we?
Let's start with the first and maybe the most important principle. It's an idea that completely flips the traditional chip design process on its head. They put the software first.
Okay, this is a total game changer. Groq designed the software, the compiler that tells the hardware what to do, before they even started designing the chip itself. Think about that. It means the software is the conductor and the hardware is the orchestra, following its every command. So instead of developers wrestling with those complex kernels for every new model, they use one simple, universal compiler. This makes everything faster, simpler, and lets developers actually focus on building cool AI instead of fighting with the hardware.
So the software's the boss. Now what? How do you build hardware that can keep up? Well, you get rid of all the traffic. The second principle is the heart of the LPU, and the best way to get it is to picture a perfectly tuned factory assembly line.
Imagine data just flowing down this conveyor belt. At each stop, a little processing unit gets its orders, grabs the data it needs, does its calculation, and puts the result right back on the belt for the next station. Everything moves in perfect rhythm. There are no traffic jams, no one's waiting around for a part to arrive. It's just pure, uninterrupted, high-speed flow.
And this really shows you the difference in philosophies. The LPU is this clean, elegant assembly line. A GPU? It's more like a chaotic hub-and-spoke model, where data is constantly being fetched from a central warehouse and sent back, creating all sorts of congestion. The LPU's design just eliminates that chaos entirely.
Of course, an assembly line only works if every single station knows exactly when the next part is coming. And that brings us to the third big idea. It sounds a little technical, but the concept is beautiful in its simplicity. It's called deterministic compute.
Deterministic just means everything is perfectly predictable, down to the exact clock cycle. That software compiler we talked about, our orchestra conductor, it knows with absolute certainty how long every single task will take. And how is that possible? Well, because in that assembly line, there's no competition for resources. No one's fighting over the same tool or waiting for the same data path. There are no surprise delays. The whole system just hums along in perfect, pre-calculated harmony.
Okay, our assembly line is smart, it's efficient, it's perfectly timed. There's only one last potential delay we need to crush: the time it takes to get the raw materials to the line in the first place. And this leads to the fourth and final principle: putting the parts warehouse right on the factory floor.
This is a really, really big deal. GPUs keep their memory, their data warehouse, on separate chips. So every single time a processor needs a piece of data, it has to take a trip off chip to go get it. In computing time, that's like driving across town. LPUs, on the other hand, build the memory and the compute units right next to each other on the same piece of silicon. That crosstown trip is gone. It's now like reaching over and grabbing the part you need. It's practically instantaneous.
All right, we've gone deep. We have a software-first design, a predictable assembly line, and a warehouse that's right on the factory floor. So, what does it all add up to? Well, this is where it gets fun. The numbers are, and I'm not exaggerating, absolutely staggering.
Because that memory is right there on the chip, the LPU has a memory bandwidth of 80 terabytes per second. Just let that sink in. 80 terabytes of data every single second.
And to really understand what that number means, just look at this comparison. The LPU's 80 terabytes per second is a full 10 times faster than the memory bandwidth on a high-end GPU. This isn't just a small step up. This is a monumental leap forward that changes what's possible with real-time AI.
Oh, and here's the kicker. All that simplicity, that elegant design, it doesn't just make it ridiculously fast, it also makes it up to 10 times more energy efficient. In the world of chip design, getting way more speed for way less power is the holy grail. It's a massive win-win.
So this is clearly a huge breakthrough. But you might be wondering, is this just a temporary lead? Will competitors just catch up next year? Well, from the looks of it, this advantage is designed to last.
See, the LPU's speed doesn't come from some fancy manufacturing trick. It comes from its fundamental design. Get this, Groq's current chip is actually built on an older 14-nanometer process. In chip making, smaller is better. As they move to a modern 4-nanometer process like their competitors are using, that already massive performance gap is just going to get wider. This is an advantage that's baked right into the architecture.
What we're looking at here is hardware that could essentially solve the speed problem for a whole class of AI applications. We're talking about a future with truly instant, conversational AI, incredibly complex simulations, and things we haven't even dreamed of yet. And that leaves us with a pretty profound question to think about. If raw computing speed is no longer the main problem, what's next? What becomes AI's new frontier?